working on the reaction system with Brian. A little bit of outline what we're doing today. We're going to go over the introduction, some objectives that we had going in, the theory behind some of the calculations that we made, our experimentation, our methodology, the results, conclusions, and some recommendations. This is the reaction. It's a denture cleaner, which is just the reaction between sodium bicarbonate and citric acid to make sodium citrate CO2 in the water. So the objectives we have were to determine the activation energy, determine the reaction order, the rate constant K, which will vary with temperature. So we're going to investigate the impact of temperature and the impact of 3 different brands that we tested out. In order to find the activation energy, you assume that it falls in a radius type equation. So if you divide the rate at one temperature by the rate at another, you get this, and you can solve for the activation energy. So that's how I solve for the activation energy for each brand. So we ran each trial at 3 temperatures. As far as the kinetics go, basic nth order rate equals some constant of the concentration of the CO2 that was being evolved to the nth order. If you take the rate as equaling the change in the concentration over time, and take the natural log of both sides, and that's what you get, and you can determine the rate constant and the order of the reaction by plotting this term versus this term. So what we did was recorded the temperature of the water before we dropped the tablet in. We recorded the time that it took to react completely for all the tablet to disappear. And we recorded the mass of the tablet and the starting and ending mass of the solution. And so you get this, the mass of the tablet minus the change in the mass of the solution is the mass of the CO2 evolved, and from that you can get the number of moles of CO2 that evolved. So you can get the concentration versus time data. And some of the results that we had, obviously for all of them, as the temperature increases, the rate increases, or the time that it takes to react decreases, so the rate increases. That's pretty much what we have for results. In terms of the activation energy, brand A had an activation energy of 446.54 joules per mole. Brand B was 676, and brand C was 174. With temperature, you see that the time that it takes to react decreases. It's just a graphical representation. Brand C, overall, reacted the fastest at all given temperatures, which makes sense because it had the lowest energy of activation. And so, as a conclusion, brand C reacts the fastest. The rate increases with temperature. We can't determine the order of the rate constant at this time. Our initial idea was to measure the amount of CO2 that was coming off by mass, but our scale goes to 0.1 grams, and that was close to the maximum CO2 that was being evolved. So we need something with a little bit more accuracy. Questions?